Hello everyone, I am Chakri Cherukuri. I work in the quant research group at Bloomberg in New York City. We extensively use Jupyter notebooks for all our research projects. And we also contribute to the Jupyter project, mainly on the widget libraries. We created a 2D plotting library called bqplot, which is open sourced on GitHub. In today's talk, we'll see how we can visualize machine learning models in the Jupyter notebook. The outline of my talk today is as follows. I'll first give a brief overview of the widget libraries I'll be using in my example notebooks. And then I'll walk you through the code of a simple example of an interactive plot so that you understand at a high level how to assemble these widgets and how to link them to create interactivity. And then we'll go through a few machine learning examples and algorithms. I'll start with theoretical machine learning examples like kernel regression. We'll see how interactive visualizations can help us better understand and interpret these models. And we'll also see the impact of hyperparameters on the regression fit. And then I'll show a nice animation of k-means clustering. Both these examples are implemented in NumPy, right in the notebook. And then we'll look at more advanced and applied use cases. We'll look at dimensionality reduction techniques applied on the yield curve dataset. And finally, we'll look at a graphical tool for doing the end-to-end pipeline of a deep learning model, right from selecting the network parameters and setting up the network architecture and the whole training process and diagnostic plots. We did a similar talk last year where we showed examples of advanced applications and dashboards. But unfortunately, all the examples we showed at that time were Bloomberg proprietary, so I could not share the notebooks. So for today's talk, all my example notebooks and all the code is available online on my GitHub account. So please feel free to download the examples, and you should be able to rebuild all the examples which I'm going to show today. Okay, the widget libraries I'll be using today in my example notebooks are ipywidgets. So ipywidgets are core UI controls like text boxes, sliders, drop-down menus, etc. And then bqplot. Bqplot are again 2D plotting widgets which are built on top of the same ipywidgets infrastructure. So they use the same traitlet mechanism for binding the attributes of widgets. So bqplot and ipywidgets can be seamlessly integrated to build rich interactive visualizations. Let's now look at an example. So let me zoom in a bit. So here I have an example of a simple plot of a Gaussian density, and we want to see the impact of mu and sigma, the location and scale parameter on the plot of the Gaussian density. Let me walk you through the code. I'm doing some imports from ipywidgets, and you notice that I'm using the pyplot API of bqplot, which is very similar to the matplotlib's pyplot interface. It's a simple context-based API. So I'm creating two vectors, x, and y is just the norm PDF of x. And then I create the plt.figure, which returns a figure widget. And then I'm calling plt.plot, which renders a line plot. I'm passing the x and y attributes. And this returns the line object, which I'm storing in PDF_line. Right? We'll need this line object later to update the y attribute. And then I'm creating two float sliders to represent mu and sigma. And I'm going to use an edge box, which is a layout class in ipywidgets, to horizontally stack these widgets. So you see that you have two nice sliders here representing mu and sigma. And finally, I want to put all the widgets in a nice layout using a VBox. Oops. So here we have a nice simple dashboard where we have the plot of the Gaussian density, and we have 2 sliders. Obviously, nothing happens when I move these sliders. So let's go ahead and link them. And this is a crucial step. To link widgets, I first need to define a callback. So I'm creating a callback called update density, where I'm fetching the new values of mu and sigma from the sliders. And then I recreate the norm PDF using the new values of mu and sigma. And then I assign the output of that directly to the y attribute of the PDF line. And this is a crucial step. In ipywidgets and all the widget libraries, we always update the widgets in place. We don't recreate them. We don't re-render them. All we do is just update the attributes in line and in place. And this triggers a redraw in the plot. And similarly, I would like to update the title to reflect the new values of mu and sigma. And finally, I need to register this callback with the sliders. So I do that using the observe method, where what I'm doing here is, once I update the value attribute of the slider, I update when I move the slider, right? I would like to call this, invoke this callback, which redraws the plot. So that's it. And now we have a nice interactive plot which responds to the sliders, right? So to summarize, this is a very simple example, but the concepts are very powerful. Once you understand how to assemble these widgets and how to link them, you can just scale them up to build rich interactive visualizations. Let's now look at some machine learning examples. The first example I have is kernel regression. So kernel regression goes by different names. You can call it local regression or non-parametric regression. The idea here is we are trying to compute the conditional expectation of y given x in a non-parametric way. It's very similar to the standard polynomial regression, except that instead of assigning equal weights to all the samples, we create a localized behavior by assigning weights based on a kernel function. So order 0 is just a simple local weighted average with the weights coming from the kernel function. And order 1 and above are weighted least squares compared to the ordinary least squares, which we do in the polynomial regression. There are a lot of choices for the kernel functions, and the most popular is the Gaussian kernel. So Gaussian kernel has infinite support, and the weights decay exponentially as we go far away points. And this truly causes the localized behavior. And we have a hyperparameter called bandwidth, which controls the bias variance trade-off. So let's now look at a visualization which helps us understand this local regression. Yeah, so here we have a nice visualization of kernel regression. Let me explain the components. I have a slider which controls the kernel bandwidth. Kernel bandwidth is the standard deviation of the weighting function. And here we have the weighting function, which is a Gaussian kernel. And here I have the scatter plot of x and y, and we have the regression fit. And we can also control the polynomial order using this integer slider. And I can also display non-parametric standard deviation bands, which act as confidence intervals, right? So let's see the impact of this bandwidth on the regression fit. When I reduce the bandwidth, what happens is we get a truly localized behavior, right? The Gaussian kernel almost becomes like a Dirac function, and what happens is we totally overfit, because this almost becomes like a one nearest neighbor, right? And as I increase the bandwidth, we see that we are able to fit better. But once I make the bandwidth really high, like in theory when I make it infinity, what happens is the Gaussian kernel becomes like a uniform distribution, and you just recover the polynomial regression. So order 0 is just the intercept, and order 1 is the linear model, etc. So as you can see, we can clearly understand the impact of these hyperparameters on the regression fit. So let me make this a reasonable value here. And now let's see how we can improve the fit. We can see that order 0 is doing a flat extrapolation, and we see some linear bias in the data set here. So let me make it order 1, and we see that this captures the linear bias in the data set. But we also see some convexity bias here. So if I make it order 2, you see that the order 2 polynomial captures this nicely. And we can also, bqplot is interactive. I can see the impact of outliers by clicking and adding points here. You can drag points and to see how extrapolation works, right? So it's very interactive. You can play with this visualization to fully understand how this regression model works. And you can also look at the standard deviation bands to get a better picture on the confidence intervals surrounding this regression fit. So that's all I have for local regression. Let's now look at k-means clustering. Here I'm implementing a Lloyd's algorithm, which is a heuristic algorithm for k-means clustering. Because the optimization problem is NP hard, the algorithm is bound to get stuck in local minima. And we'll see, I created a retry button so that we can click on the button and try out different centroids to see if we can get out of the local minima. The whole algorithm is implemented in NumPy right here. So let me explain these sliders. I have a slider called points to control the number of points. And then I have a slider to control the number of clusters. And I also have a slider to control the cluster standard deviation to see how closely or how far away the clusters are. Let's start the animation. We see that in 5 iterations or 6 iterations, it was able to. Okay, here we see that the algorithm got stuck in the local minimum, right? So let me try to recenter the centroids, and you immediately see that it was able to fix the problem. We can now try for different, again we see that the algorithm got stuck in the local minimum, and we can try to recenter the centroids, and hopefully that should fix the issue. So as you can see, these kind of interactive visualizations are extremely helpful in kind of understanding these kind of theoretical models, and they can be used as training aids in helping explaining these kind of algorithms to students. Okay, so let's now look at some more applied examples. We look at dimensionality reduction applied on yield curve dataset. So a quick primer on US Treasury yield curves. US Treasury, as you all know, issues bonds with different maturities. So we have they issue bonds with short-term maturities like 1 month, 3 months, or 6 months, and they also issue bonds with long-term maturities like 10 years, 20 years, and 30 years. So what is a yield curve? Yield curve is just the plot of the interest rates on the y-axis and the maturities on the x-axis, right? So US Treasury has 11 maturity bonds. So the yield curve has 11 points. And the data set I'm using here is the time series of these 11 interest rates, because these time series, they change every day, right? And you can easily download this data set from the US Treasury website. If you look at this picture, we see that the shape of the yield curve changes every day, and especially with different regimes, the shape totally changes. For example, if you look before the crisis, we see that all the interest rates were pretty much hovering around 5%, so the yield curve is pretty much flat. And after the crisis, because of quantitative easing, all the short-term rates were pushed down. So we have this kind of shape here, right? And recently, the rates have been globally going up. So we have a shape in yellow here, which is somewhere in between the pre- and post-crisis levels. So given this highly correlated 11-dimensional data set, the question is there any parsimonious representation possible, either to model the dynamics of the data set or for data visualization? And we have a couple of techniques. The classical technique is called principal component analysis. So what PCA does is it takes this 11-dimensional data set in this example and creates new factors which are linear combinations of all these 11-dimensional data set. So each factor is a different linear combination of these 11 inputs, and we form such linear combinations, and typically we need 3 to 5 factors to explain almost all the variance in the data set, and that's how we get the dimensionality reduction. And we also have newer techniques which are based on deep learning. There is a technique called autoencoder, which is based on a neural network. And what we are trying to do here is we'll take the 11-dimensional input and try to compress it into 2 or 3 dimensions. And this part of the network is called the encoder, where we try to create a compressed feature vector by reducing the dimensionality from 11 to 2 or 3. And in the decoder part, we try to reconstruct the original yield curve by expanding the dimensions. So this is called the decoder component. And because it's a neural network, I can create nonlinear activations after each layer to capture nonlinear dynamics in the data set. For example, if all my activations are linear, I pretty much recover PCA because I'm just taking all the linear combinations, right? So PCA is a special case of an autoencoder, and with autoencoders, we can also capture the nonlinearities in the data set. Before we try to apply PCA and autoencoder on the original 11-dimensional data set, let's try to do some data visualization and try to understand if are there any nonlinearities in the data set which warrant the use of an autoencoder, right? Before we start applying these fancy models, we need to first understand whether it makes sense. Why not just PCA? So to help us answer those kind of questions, let's look at a nice data visualization. Adjust the zoom. Okay. So we have a interactive visualization which was built entirely in bqplot. Here I have the time series of all the 11 bond interest rates, right? You see that globally the interest rates were around 5% before the crisis. And as we go into the crisis, we see that all the short-term interest rates were almost around 0. And more recently, the rates have been going up. So you have this kind of interest rates here. And obviously, we cannot visualize the cloud of points in 11-dimensional space. So what I'm trying to do here is take 2 canonical points on this yield curve and try to understand the relationship between those 2 points. And the points I'm choosing here are 2-year and 10-year interest rates. They are so important that the spread between the 10-year and the 2-year interest rate is actually used as a proxy to display the shape of the yield curve. So these are very important points which represent the short-term and the long-term interest rates. And what I'm trying to do here is to look at a scatter plot of these 2 points so that we can visualize the data set in 2 dimensions as opposed to 11 dimensions. Notice that I'm also using the color scale to represent chronology here. So points in red are, I think, around 2006, where interest rates were typically around 5%. And as we go into the crisis, the rates went down. And again, you see the rates going up, and green is the more recent period, right? So using the color scale to represent chronology is a very nice aspect of bqplot. Now the question is, let me look at some slices of time periods to understand the relationship between these 2 points. So, okay, so this is before the crisis, and you see the relationship is pretty much linear, right, between the 2-year and the 10-year points. And if you go past the crisis, you again see the relationship is linear. And if you look at a more recent period, you see the same structure. There is a linear relationship between 2-year and 10-year yields. So where is the nonlinearity creeping in? So nonlinearity creeps in when we try to combine regimes. When I combine post-crisis and the current periods, that's when you see the nonlinearity. So here the rates were around 3%, and they went down, and they again started going up. And we have this V-shaped nonlinearity, which comes into play when we combine regimes. And these kind of data visualizations are extremely important in trying to understand the relationship between points in lower dimensions. Again, when I combine the pre-crisis and the post-crisis levels, you see the nonlinearity in the data set. So what we'll do now is let's try to fit a 1-factor PCA and a 1-factor autoencoder on this reduced dimensionality data set and see what happens. So I'm loading pre-trained models here to save time. We clearly see that the autoencoder in magenta is capturing the nonlinearity, whereas PCA, being a linear model, cannot capture this nonlinearity, right? And similarly, when I go here, we again see that autoencoder nicely captures this nonlinearity in the data set, the V-shaped structure, whereas PCA just cannot do that. So now that we have convinced ourselves that there is some nonlinearity in the data set, and autoencoder can potentially do much better than PCA, let's now try to compare them on the whole data set. I'm again using pre-trained models. I didn't want to spend time training the models here. So here what I did was, in the last example, I took a 2-dimensional data set and fit a 1-factor PCA and 1-factor autoencoder. But now I'm fitting the PCA and autoencoder on the whole 11-dimensional data set. And I'm doing a 2-factor PCA and a 2-factor autoencoder. And we want to compare the results of PCA and autoencoder on the whole data set. So for training, I'm using this whole data set all the way till 2017. And for testing, I'm using the more recent period. And this is truly out of sample. The models are not trained on this data set. And we want to compare PCA and an autoencoder on this out of sample data set. So now the question is, how do we compare PCA and an autoencoder? So what we are doing here is we are compressing the data set from 11 dimensions to 2 dimensions, and then reconstructing the whole yield curve back to 11 dimensions from the 2-dimensional compressed feature vector. So the best way to compare them is to see how good the reconstruction is of PCA and autoencoder. And since we already know the actual yield curve, we can overlay all the three yield curves, the reconstructed yield curves and the original yield curve, and see how closely PCA or autoencoder track these yield curves, right? I'm going to use a nice tool called date selector to select different dates and see how the reconstructions compare. So the true yield curve is in yellow, and we see that autoencoder closely tracks the true yield curve compared to the green PCA. And we can look at different dates and see that globally the autoencoder, as expected, is doing a much better job. But obviously this is the training samples. So let's now go to the test data set and see how they are doing. And we again see that autoencoder is doing a much better job in tracking the original yield curve compared to the green PCA. Let's now go to the more recent periods, and we see a problem. Both autoencoder and PCA are not doing a great job in tracking the yellow yield curve, and the reason is obvious. We haven't encountered this kind of data in our training samples, right? We trained the data set mostly on the pre-crisis and the post-crisis levels, and we are in a totally different regime now, and no wonder PCA and autoencoder will not do a great job in tracking the yield curve. So again, these kind of tools where we can quickly scan through different time periods will help us understand where the model is doing well and where the model is not doing well. And now that we understand that we can't just be happy training our models on some historical data set and hope the models to perform consistently well going forward, especially in time series, we encounter regimes where we encounter different trends or the dynamics of the data set changes. So we need to keep on doing the training process on a rolling basis so that we capture all these dynamics. And these kind of tools can help you clearly understand where the models are doing well and where the models are not doing well. So that's all I have for the dimensionality reduction. So let's look at our last example. So we'll look at a graphical tool for doing the end-to-end pipeline of a deep learning model. And I built this tool entirely in Python using object-oriented techniques with a plug-and-play architecture. So I just built it as a prototype, but the idea is you should be able to easily extend the base classes to provide your own training plots and diagnostic plots. I provided basic implementations, and you could easily customize them according to your requirements. For example, I provided implementation of regression diagnostic plots, but you can easily extend the base class to create classification diagnostic plots, where you can add, for example, interactive confusion matrix, where you can drill down on specific cells and further access the misclassified points like that. And I'm also directly introspecting on the Keras library to build all the UI components, so they are not hard-coded. And so let's go ahead and look at this tool. The data set I'm using here is a simple toy data set based on the Black-Scholes formula. So what is Black-Scholes formula? It's a smooth nonlinear function of 4 numerical inputs, and it returns a numerical output, which is the price of an option. What we are trying to do here is trying to learn the Black-Scholes formula using a deep learning model. The data set is manually generated using the formula, so there's nothing special about it. And okay, so we have this tool here. Sorry, I'm not a UX expert, so a lot of enhancements that can be made to this. So the first tab here shows the network parameters. We can select the number of epochs, and we can select the batch size for each epoch. and you can choose from a bunch of loss functions. These are all directly obtained by introspecting the Keras library, and you can choose from different optimizers, and for each optimizer you can also see that the defaults are automatically populated, so you can pick from them, right? And since this is a regression problem, let me pick mean squared error, and I'll use Adam, and let me give a learning rate decay to the training process. And now we can select the architecture. I'm providing support only for fully connected layers here, but you can easily extend this to support convolutional layers or LSTM cells, etc. Notice that the tool automatically infers the number of inputs and outputs by looking at the inputs, the training data set. So let me add a bunch of hidden layers. And we can choose from different activation functions. So let me pick tanh. So tanh is a monotonically increasing function which goes from -1 to 1, and that creates the nonlinearity in the data set in the modeling. So 1 second. Yeah. So let's now train the model. We see that the loss and accuracy curves are getting updated in real time as the training is going on. Oh, wow. We see that the training stalled initially for 25 epochs, and then it starts learning and the accuracy starts shooting up. I'm using R square as a metric for this problem, and we see that there is some good improvement in the training process. So we are done with the training, and now we can look at the distributions of weights, biases, and activations. So here we are kind of peeking into the black box of the deep learning model. We are trying to understand how the training loss curves are getting updated in real time, and also we can look at the distributions of weights, biases, and activations. We can look at them for different layers and for different epochs. So if you look at the weights, they're initialized to uniform, and as I go into the training process, you see that they converge, which is good. And you can also look at the distributions of activations here. Since tanh goes from -1 to 1, most of the values are either -1 or 1, and you see some values in between. Okay, so if you look at the last layer, you clearly see a problem, and the problem is the saturation of activations. What's happening here is the activations are either -1 or 1. So what happens when the activations are -1 or 1? The gradients are 0, right? Because we are in the flat region of the tanh. So the gradients are 0, and that means the gradients are not flowing back in the backprop, and that explains this stalling in the training process, right? And so if you look at these kind of plots, you get an intuition behind why exactly the training process is stalling, or what is happening with my activations, right? And if you notice, after I go past 25 epochs, right, you see the activations are no longer saturated. That means the gradients are non-zero. They're flowing back, and the weights are getting updated, and the training is going on. And that explains this behavior here. And then you immediately start the learning process, and it's because of this, right? And finally, we can look at the diagnostic plots. Now, this looks horrible because so let's go and change the activation to ReLU, which has much better convergence, right? So let me go ahead and retrain the model. So now we see that the accuracy immediately improves. ReLU is a much better choice for an activation function, and it's obvious when you look at the loss and accuracy curves. You're almost done, and you immediately see that the accuracy is approaching 100%. and the distributions are very nice. They're well, there's no saturation anywhere, right? And let me show you one final improvement which we can make to really improve the deep learning model. Deep learning models typically expect the inputs to be small numbers in the range from 0 to 1. So transformation and scaling of data is crucial, and we'll see that now. Let me just use the scale data set here. So what I'm doing by scaling is I'm subtracting the mean and dividing by the standard deviation, so that all the numerical values across all the features have similar dimensions. Unfortunately, I have to rerun this tool. Ideally, we can have an extra tab for doing data cleaning and data transformations, but let me just run it for around 30 epochs. I'll keep the same architecture. Right? And let's do the training. You see immediately the accuracy shoots up to 100%. And so, transforming the data is crucial. As we can see, we can only tune the hyperparameter so much. The first thing is make sure your data is transformed well. And if you look at the diagnostic plots, they look much better. So again, to summarize, I just created a simple prototype to show the value of these widget libraries, what you can accomplish with these kind of widget libraries. And if you spend enough time, you can make it an industry-grade neural network builder with all the bells and whistles and support for all the activations and different layers and all these things. Time. Yep, so that's all I have for today. I hope you found these examples instructive and useful. I want to thank you all for attending my talk. And if you have any questions, I'm happy to take them. Yeah, so let me send you the link. It's on my GitHub account. All the examples and pretty much everything I've shown here is all available here, so you can just download from here. Yeah.
Library works in Jupyter Lab also?
Yeah. Actually, all the examples I've shown run in a nice, beautiful black theme notebook. So if you try this in white theme, it will not look this good. But hopefully with the Jupyter Lab, I think black theming also will be enabled. So you should be able to take advantage of that. Yeah. Yeah.
Okay, example, you compare the PCA and the Autoencoder. Was there any reason that you selected those two features, 2-year and 10-year?
Yeah, because 2-year and 10 years are like a very important points on the yield curve, which represent the short-term and the long-term bonds. And I was mentioning before, the spread between the 10-year and the 2-year is used as a proxy for the shape of the yield curve. So I just picked the most important points. Yeah. Thank you all.
All right, thanks, guys. Thank you so much.